Hi, in this video we're going to talk some about theorems about limits. So before we actually get into the theorems, I want to talk a little bit about why we need theorems. We've already talked about limits in a couple of different ways. The first way we talked about limits was using graphs, and that works great as long as the graph that we have is labeled precisely and is accurate. But especially if you're given a function equation and you might type that into a graphing calculator or some kind of app that graphs it, the algorithm that creates that graph is using decimal approximations. So sometimes you don't always have a precisely labeled graph. The other way that we talked about limits was using tables. And we plugged in some numbers, both larger and smaller than whatever value we were approaching, and we were able to use tables. So with tables, again, you're generally getting decimal approximations out, and so that really only allows you to estimate a limit. And so if you have a limit that is perhaps something that is difficult to estimate precisely, either from using a graphing calculator or a graphing app or a table, so something like where the answer for the limit problem is like pi over 7 or natural log of 2 or something like that, then you need something else. You're not going to be able to get that precisely from a table or a graph. So that's what theorems allow you to do, is to calculate limits more precisely and really allow us to find limits analytically. So sometimes you'll be asked to show analytic steps to find a limit, and that's what they're talking about, is really using theorems. Whenever we do that, we often want to check that what we get makes sense by perhaps using a table or graph, but the idea is that theorems allow you to do things that you wouldn't be able to do from just a table or a graph. Alright, so we're going to talk about several different theorems here, and then there are more that we'll learn later in the course. So this is just kind of the introductory set of theorems that we're going to look at. One thing that you might remember from previous math classes is that theorems are really things that can be proven, not just make an argument or draw a picture to understand why these things are true, but theorems can actually be proven theoretically. We are not going to be able to do that quite yet. We need some more definitions that are actually in the next section of our textbook, so we will look at those later. But for right now, we're going to just state the theorems and maybe draw some pictures to understand why these theorems are correct, and then we will prove them when we get some more theory a little bit later. Alright, so this first theorem is about a very specific function, the identity function, f of x equals x. And so that is a function that we do have a good picture of what the graph looks like. You know what the graph of f of x equals x looks like. That's a straight line through the origin with slope 1. It's just the line y equals x. And so that's a function that we know a lot about, and so we do have a graph that we can label precisely, so we can think about why this theorem is true by using the graph. Again, that's not really a proof, but we can at least think about why this theorem is true. So if I think about my function f of x equals x or y equals x, and I think about some point at x equals c, and I think about what's happening on that graph when x is close to c, so that's the graph y equals x, so every point has the same input as output. And if I think about being on that graph and going from the left and from the right and letting x get closer to c, you can just think it through and understand that the y values are also going to get closer to c. So that's an argument for why this theorem makes sense. Again, we will prove that later. Alright. So that's a pretty simple one. We don't feel like we maybe necessarily even need a theorem for that kind of limit. We could just think about it graphically. Same thing really with the next one here, limit of a constant function. So again, this is one where you know what that graph looks like. This is just, you've got your x and y axes, and then if you think about that, that's the line y equals k, where k is some constant. So it's just a horizontal line at whatever that y value of k is. And then if I think about getting close to some point on the graph, when x is getting closer and closer to c, and think about the point on the graph, that we're getting closer and closer to when x gets closer and closer to c. That point on that graph would be at c comma k. And so as x gets closer to c on both sides, the y values are at and also get closer and closer to k. Right? So that's another one where we can just kind of think about the picture and understand why that theorem is true. So on the basis of those two functions, we might say, well, okay, that makes perfect sense, but why do we need theorems? We can think about the graph. So the real power is that these two functions are sort of basic building blocks. And so if I think about taking those two really basic sort of functions and then combining them in lots of different ways, we can get all kinds of new functions. And so that's what the next few theorems are about, thinking about combining functions. So there's a lot of parts here on this theorem. So it talks about if I have two functions that I know the limits of, so this might be at this point our kind of two basic building block functions, our identity function and our constant function, and I know those limits, then there are all these different ways that I can combine those two functions and get limits of new functions. So this would allow you to think about limits of functions that are not just the identity function or a constant, but some combination of them. So for example, if I wanted to think about a function that was x plus 5, that's an identity function plus a constant function. And so I could think about combining those two functions using a sum. All right, and so these theorems actually do require some proof, and we will prove that when we get to the next section. But for right now, we're going to just practice using these theorems. So the first one here says if I know the limit of two functions exists and is a constant, then as long as I'm approaching that same value, notice on all of these that x is approaching the same value that we already knew about, then if I'm finding the limit of the sum of those two functions, I just get the sum of the limits. All right, and then kind of similarly, we've got a difference rule for subtraction. We've got a constant multiple rule, so that k is some constant times a function that we know about. Then I can just take that k times the limit of the function that we're working on. A product rule for a product of two functions. Quotient rule for a quotient of two functions. Notice on that one it does mention that the limit on that denominator should not be 0. If the limit on the denominator is 0, that may or may not mean the limit exists, but it means we can't use this quotient rule to find it. And then this last one has a lot there, but power rule. So it's limit of a function that we know about to some power, and notice that that power is a fraction. R and S are integers with no common factor, so S could be 1, so we could have a whole number exponent here, but S could also be something other than 1, so we could have things like fraction exponents, which allows us to find limits involving radicals. S is not 0, and L to the R over S is a real number. Okay, so we're going to use some of those theorems to find some limits. There's one more set of theorems that I want to point out before we get to that though, so let's look at that one next. All right, so the next thing in your packet of notes here talks about substitution shortcut theorems, and these are ones that you are going to use a ton. So these theorems, often when it's asking you what theorem you've used, this will be one that you'll use quite a bit. All right, so these are the result of some of those previous theorems about combining functions. So if we think about a polynomial would be something like 3x squared plus 4x plus 5 or something like that. And so you can think about that that's really constant functions and identity functions. If you think about x squared, I can think about that using that power rule, or thinking about that as x times x. But that's a sum and product of a bunch of those basic building block functions. So polynomials are really constructed out of identity and constant functions. And so instead of combining them in all those different ways, I can sort of state this global theorem about polynomials. It says if we're working with a polynomial, then the limit as x approaches c of that polynomial is p of c. And so these are called substitution shortcut theorems because you're just able to substitute that value that x is approaching into the function. So one important thing to remember, sometimes when students learn these theorems, they get a little distracted. One important thing to remember is that this is not what limits are really about, but sometimes you can use this shortcut, which is handy to use. We talked in the videos that we did earlier for this section about that the limit as x approaches c is asking about what happens when x is close to c, but not at. And p of c, so when I actually plug a number into a function, that's about what's happening when x is at c. And in general, that's not necessarily the same thing. That's not really what limits are about. But what this part of this theorem says is that for this kind of function, polynomial functions, those are actually the same thing. Some textbooks I've taught out of, instead of calling these substitution shortcut theorems, they'll talk about this as theorems for nice or well-behaved functions. Okay, so polynomials, we can use substitution shortcut. Rational functions, it says if numerator and denominator are polynomials, provided the denominator, q of c, is not 0, then we can do that same substitution shortcut, just substituting that value in for the numerator and denominator and getting that answer. Next part here, transcendental functions. So these are functions that are not really polynomials or rational functions, but that also are nice or well-behaved. Again, stating this theorem is not proving it. We will look at that when we look at some more theory. But we see it says as long as the value that we're getting close to is in the domain of the given function. So we spent some time reviewing domain. This is part of why. As long as that value is in the domain of the given function, then for all these different, we see a bunch of trig functions, e to the x function and ln of x function, that you can just substitute that value into the function, provided it's in the domain. All right, and then one more here, and then we'll look at some examples. So composition of functions. So if I know the limit of the inside function, and then one thing to note here, notice that on this second limit, x is approaching L, which is the value of the limit for the inner function, then I can also use this composition. So that allows us to think about things like if I had sine of a polynomial function, and allows us to combine these other functions that we have in some different ways. All right, let's look at some examples here of using these theorems. So here are 3 different examples that we're going to use theorems to find these limits. And one thing that I really want to emphasize here is that I'm asking you to state which theorems you are using. Our online homework doesn't generally ask you to state the theorems, but in the written work that I'm going to ask you to do, I'll often ask you to state which theorems you're using. So this is an example of what I would expect you to do for something like that. Okay, so when I look at this first problem here, and I'm going to use theorems to find this limit, one thing that I want to think about is which theorem applies to this. So I'm going to just scroll back up here and look at the ones that we had just above this. We have a few functions here with special names: polynomials, rational functions, transcendental functions. And this first example we were looking at, our function is 3x plus 1. So that's actually a polynomial function. So for example 4 right here, I'm going to notice that this is a polynomial function. You don't necessarily have to write this, but that substitution shortcut theorem for polynomials says that I can go ahead and substitute x equals 2 into the function in place of x and then simplify it and get my answer here. All right, so which theorem did I use? And this is the step right here where I wrote equals, where I used that. I used the substitution shortcut theorem for polynomials. All right, so I don't usually want to write all that out, so I will often abbreviate that by writing SST for substitution shortcut theorem. There are a lot of different parts for that substitution shortcut theorem, so which specific part that I used was the one for polynomials. So I'll often write something like SST poly for substitution shortcut theorem of polynomials, just abbreviating there. Notice that there are different theorems that you actually could cite here. If I think about that 3x plus 1 as 3 times x and plus 1, you could also think about that as combining 2 different constant functions, 3 and 1, and then combining that with the identity function, x, using multiplication and addition. So you could also say that you have used the theorem about the identity function, the constant function, and then the combining functions theorems about addition and multiplication. So that's citing a lot of different types of theorems here, and it's maybe more concise just to say that you've used that substitution shortcut theorem for polynomials. So that's probably what I would write. Notice also that on one like this that you should be able to think about whether that answer makes sense. This is one where you know what the graph of this function looks like. It's a line, y equals 3x plus 1, y-intercept is 1, and slope is 3, so it's pretty easy to get an accurate graph of that. And if you think about the graph of that when x is close to 2, you should be able to think about there's a point at 2, 7, and as you get closer and closer to 2 from the left side and the right side, the y values get closer and closer to 7. So just using the graph to sort of double check that my answer makes sense here. All right, let's look at this next one and think about using theorems. So again, this is a polynomial. So I'm going to write equals, and then I'm going to label what's allowing me to say equals, and that's a substitution shortcut theorem again for polynomials. And I'm going to just substitute -2 in for x. Be careful when you do that you square the 2 and the negative, and I get 4. So substitution shortcut theorem for polynomials. Again, I could also use the identity function and combining functions with multiplication, but substitution shortcut theorem for polynomials is probably a more direct way to say what you've used. Again, thinking about the graph, y equals x squared is one that you know what the graph looks like pretty easily, and you can think about when x is close to -2, what is going on with the graph, right? And the y values are getting closer and closer to 4 as I get closer and closer to x equals -2 on both the left and the right side. All right, again, remember, substitution is not really what limits are about, but it is really handy when we can use this shortcut to get the answer for nice, sort of well-behaved functions. Those first two are functions that you know a lot about and know what the graph looks like. This next one is one that you probably don't know what the graph looks like, and it's actually kind of difficult to get a really precise graph even from a calculator or computer. So this last one is one where it's really helpful to actually use the theorems. All right, so I want to think about what kinds of theorems I could use here. So I'm going to scroll up here and look at what we've got here. So rational functions, sometimes students look at that and they notice I have this fraction expression here, but notice in the statement of that theorem says that the numerator and denominator have to be polynomials, and our denominator of our function we're looking at is a polynomial, but the numerator is not. Polynomial is made up of powers of x, so our numerator was sine of x. But I do have a theorem here about transcendental functions that involves sine of x. So the numerator I can think about like that. The denominator for the problem we were looking at was x, which is a polynomial, or I could think about that as the identity function. And then I had some theorems in the previous item on our outline here, 3, some theorems about combining functions. And so I did have a theorem about combining functions that involved a quotient, which is what I have here. So for this example we're looking at, I'm going to have to cite a couple of different theorems here. So I'm going to write down my work and then write down which theorems I used. So I'm using substitution shortcut theorems here. So I'm going to substitute in pi over 2. Remembering that is not really what limits are about, but when this substitution works, it's a handy thing to be able to do. All right, sine of pi over 2, just thinking about your unit circle there, is 1, and then the denominator is just pi over 2, and so when I simplify that, I get 2 over pi in exact form. All right, so which theorems did we use? I used a substitution shortcut theorem for transcendental functions, for the sine function on the numerator. I used a substitution shortcut theorem for polynomials, or I could think about the identity function for the denominator when I substituted pi over 2 into the denominator. And then I also used the theorem about combining functions. I'm going to just abbreviate that, combining functions, CF, and I used the quotient rule there. right, and remember that one important part for that theorem about combining functions with the quotient rule is that the denominator should not be 0. So notice here that our denominator was not 0, so we're good with that. The other thing that I want to point out about this one is that this example is one that it would be difficult to get this correct answer using a graph or a table. You might be able to get decimal approximations that are close to 2 over pi, but without an accurately labeled graph, which a computer or calculator is not going to be able to do for you using irrational numbers like 2 over pi, you really need theorems to get an answer like this for this kind of problem. All right, and so we'll look at some more problems too where theorems are helpful. There's several more theorems that we'll talk about, but these substitution shortcut theorems are kind of the basic building block that you will use a lot. So go ahead and watch those next videos for some more theorems.